Today we're going to take a look at log graphs. Now, I'll fill you in on a little secret. It turns out that when you graph a log, you get a set of points. And when you connect those points, you end up getting the graph of a log. What? You think that looks like a baseball bat or maybe a fish? Well, it's not the graph that you get, but you're probably not surprised to find out that there is a connection between exponential and log graphs. And that's really what we want to find out, is that connection today. Now I'm going to go ahead and just give you the connection, because it's a pretty major idea that exponential and logarithmic graphs are inverses of each other. The connection is that they are inverses of each other. Now, when we talk about a mathematical inverse, we're talking about this idea of a reflection. We're talking about this idea of switching. Okay, now we've seen these connections in other algebraic situations. We've seen it with trig functions. We've looked at it with basic algebra equations. What we're going to do is just show you how this applies today to logarithmic and exponential equations. All right, so we get to this pretty standard situation where we want to find and graph the inverse. And notice the equation that we're going to find the inverse of. It's an exponential equation, y equals 2 to the x. Now, whenever you find the inverse of something, you always want to switch x and y. And so we're going to do that basic switching. Don't make it too hard, because all you have to do is put an x where y was and put a y where x was. So we switched x and y. And after you switch x and y, you always want to solve for y, because we like equations to be y equals when they can be. Now, we're at an interesting juncture here, because the question is, how do you solve x equals 2 to the y for y? How do you solve for y when it's in the exponent? What's that, you say? Slap it with a log? Right, you want to take the log of both sides. When you take the log of both sides, it causes this exponent to come tumbling down, and we end up with the log of x equaling y, the log of 2. Now, of course, the only thing left to do to solve this for y is to divide both sides by the log of 2. Now, that does give you y equals. It's what we're seeking. But interesting, there is a way that we can interpret the log of x divided by the log of 2. I'm talking about the change of base formula. I'm talking about writing that as log base 2 of x. And when we write it that way, we have a nice, neat equation for the inverse. Okay, now the inverse equation is a log. It was exactly what we said on the other slide. So how does this all graph together? What is the graph connection? Well, if we want to graph the original equation, we should be using some ideas from a couple weeks ago. One of those ideas is that it has a starting point. That starting point is the number in front of the equation, so we can start at 1. What else do we know about this equation? We know that it has a horizontal asymptote at y equals 0. But ultimately, we need to be ready to draw a growth graph. And so we have a nice exponential growth graph. Again, it has a y-intercept at 0, 1. And, of course, it's got that horizontal asymptote. Now, the story goes here that the log graph that we're trying to create is going to have to be the inverse. It's going to have to be the reflection. It's going to have symmetry across this line y equals x. And so if we don't know what the graph looks like, we can take the existing information, such as the point 0, 1, and we can switch that. We can reflect that to be the point 1, 0. We can take the existing information, like the asymptote y equals 0, and we can switch that to be the asymptote x equals 0. Now, what I'm doing here is I'm getting myself prepped to draw a graph that's going to have the reflected behavior of the original graph. And this red graph that I just drew, well, now that would have to be the graph of the log. And in fact, that's what all log graphs look like, where they kind of go up in this early part of the domain, and then they start to level off as we get into the latter part of the domain. But nonetheless, that's our log graph, and it definitely is the inverse of our exponential graph. Here's a good problem to try on your own. I know it's just the second example, but I encourage you to try to find the inverse. It's not real hard to do. All you got to do is switch x and y and solve for y. Maybe you even want to try to graph both of your equations. All right, good time to push pause, and I'll meet you back here in a moment. All right, so how'd you do? When you switch x and y, your equation is just going to become x equals 3 to the y minus 4. Now, at this point, our goal is to solve this for y. You want to make sure you do the order of operations carefully. You should be adding 4 to both sides as your first step. But once again, we arrive at this place where we want to get y out of the exponent. Now, you most definitely can take the log of both sides. When you take the log of both sides, it causes the y to come out of the exponent. And maybe you are ready to just divide both sides by the log of 3 also. It always works that way. The thing is that when I divide by the log of 3, that's the same thing as having the log base 3. So we want to write it in that form so we can see it as a single log base 3 of x plus 4, and that equals y. It also equals our inverse, so it's probably a nice idea to write it as the inverse is equal to the log base 3 of x plus 4. Now, the whole point behind this is, what does the graph of that look like? What the heck is the graph of a log base 3 of x plus 4? Well, the answer is that it's going to be the inverse of this known graph. And the hope here is that you do know some things about this graph from a few lessons ago. You know that it has an asymptote at -4. You could plug a 0 into the equation for x, and you could get the y-intercept. That y-intercept is going to come out to be 1 minus 4. It's going to come out to be -3. So I know that. At some point, we have to be ready to graph a growth graph that passes through this intercept and that, of course, approaches that asymptote. Now, what we're going to do is we're going to take that graph, that growth graph we just drew, and we're going to reflect it to help us get the inverse graph. So we can switch x and y. We can switch the y-intercept to be an x-intercept. We now have an x-intercept at -3, 0. We can switch the asymptote, which was once y equals, to be x equals -4. Now, we have to be able to see the reflection. If you reflect this this middle part right here, you end up with a log graph that's going to have this shape. If you reflect the part that's going up, that's now going to be a part that's going out to the right. And if you reflect the part here on the left, that's now going to be a part that is going down. In fact, you only have to see a couple of these log graphs to know that they always will have this basic shape because they are the reflection, they are the inverse of an exponential graph. Two additional observations that I'd like to make now that you've seen a couple of these graphs. One is the domain. The domain is definitely restricted by this horizontal or this vertical asymptote. So it's very easy for us to say that the domain is going to be everything on the right side of -4. And the other observation I'd like to make with you is how this graph shows up on a calculator. First, to be able to type this into your calculator, you're going to have to go back to the change of base form, where essentially we take two logs and divide them. So you can type in the log of x plus 4 divided by the log of 3. Secondly, when you graph it, you don't actually get the full reflection. You don't actually get the full graph. A lot of that behavior is happening near the asymptote. And so what we want to understand is that even though the calculator is not showing it, the log graph definitely continues to go down to infinity as it approaches this vertical asymptote at -4. Sometimes students say, well, why is the calculator not showing this region over here as it goes -infinity? Calculator runs off of an algorithm. It plugs in x values and gets y values. The algorithm has stopped calling for x values because we're getting too close to this asymptote. So we have to be a little smarter and know that the graph does exist as the y values continue to go to -infinity. I said two things, but I'm going to add one more thing, and that is that you can actually look at a log equation, which we're going to do shortly, and you can say that there's been a transformation. You see, when you add 4, that's always been a shift to the left 4 units. And so if our graph starts at 1, which a log graph does, and I shift it to the left 4 units, well, I'm going to end up with this x-intercept here at -3. So what does the base do? Well, the base is really just a number that affects the specific shape curvature of the graph. Honestly, you're not going to notice any difference when you draw a sketch because the base 3 is just matching up with the growth of 3 from the original equation. So let's pause and just kind of make a general statement here about the graph of a log. And we like to refer to the common log because, as we mentioned, the base really doesn't make a big difference in your graph. So when we talk about graphing y equals the log of x, well, of course, that would be a base 10, but really what we need to be aware of here is that the graph is going to always start at and have a y-intercept of, an x-intercept of 1. It's going to have a vertical asymptote at x equals 0, and the shape of that log is always going to be such that it has this rapid growth and then a quick leveling off. And so all log graphs, particularly the common log graph, is going to possess this shape. The domain, well, it's going to be based on that vertical asymptote, and it's pretty easy to see that it'll be on the right side of 0, as we can't do the log of a negative number. Now, as one additional commentary, did you know that you are a log graph? No, silly, I'm not saying that you look like a log graph, but the growth of a human being is actually modeled by a logarithm. A typical human growth chart will always be in the shape of a log, where you have this rapid growth in the beginning when you're a toddler, and then there's this leveling off that occurs as you're an adolescent, and eventually, of course, you don't grow anymore. So what we say is that this log graph is only going to be appropriate for certain x values. And so what is likely the case is that the graph has been shifted, and the asymptote is probably over here, which it doesn't apply. And then again, since you eventually stop growing, the log equation begins to also break apart as we get out to x values in a certain age bracket greater than, well, it depends, greater than 15, 16, 18. So many things in nature can be modeled with logarithmic change. I'll be showing more of that application to you tomorrow. But for today, let's graph some logs. Let's use the idea of transformations, and we'll try to identify as much of these punch points as we can: x-intercept, vertical asymptote, domain, y-intercept with a question mark, as you'll discover some log graphs don't have a y-intercept. Now, we're going to be approaching this graphing primarily without a calculator, so it'll make for a good mathematical workout for your brain. All right, so if we want to graph the log base 2 of x minus 3, and say we wanted to find the x-intercept, well, that means that y equals 0. Oh, so I could plug a 0 in for y? Well, sure, you could. And actually, it's kind of interesting because now I have the ability to solve this equation for x. Remember, you want to pull out the ace of base. You want to base both sides with a 2. And, of course, 2 to the 0 is equal to 1. So we actually end up with some simple arithmetic that x equals 4. Now, you could have also found that x-intercept by thinking a little bit about transformations. Transformations would say that this graph would shift to the right. As long as you know that the graph originally started at 1, you could easily shift that to the right, and you would also be at 4, 0. What else shifted to the right? That's correct, the vertical asymptote. So the vertical asymptote, which started at 0, is now to the right 3. Of course, is going to be at 3. And the only thing left to do is to draw that log graph that has that rapid growth and then levels off, as all logarithms do. We could describe the domain. That's something that's typically part of a conversation about a graph. And of course, the domain this time is greater than 3, but it's always related to that vertical asymptote. Now, do we have a y-intercept? It doesn't look like we have a y-intercept based on the behavior of this graph, but if you investigate the algebra, you see here that when you plug a 0 in for x, that you're being asked to do the log of a negative number. Now, if you're still saying, I don't get it, what's wrong with the log of a negative number? Well, this is like asking ourselves 2 to what power equals negative 3. There's no power you can put on 2 to get negative 3. That's why you can't do the log of a negative number, and that's why there's no y-intercept. Here, do you want to try one on your own? I encourage you to try to find what you can about this log graph. A great start would be the x-intercept, and maybe see if you can even get a graph. Now, I know the temptation here is going to be just to let the video play and watch me do it, but try to get your brain some of that thinking, find some of these values, think about the sketch, and then watch the rest of the video. All right, so if you were going to try to find the x-intercept, you would plug a 0 in for y. You can kind of trust this behavior. It works every time. The neat thing here is that you get yourself a little equation to solve, add 2, and get ready to solve for x using, once again, the ace of base. Base 10, I hope, as since the base was not written, it was assumed to be a 10. Now, 10 squared is 100, a big old number, but nonetheless, it does produce a value that when you finish solving, you get 104. Yes, we're going to have an x-intercept at 104. Now, the y-intercept is when you plug a 0 in for x, and it looks like here that we're going to get the log of a positive number. Something that we can actually do. Now, if you're saying, but how am I supposed to do that? Well, you can't find that value without a calculator because we're trying to find 10 to what power equals 4. That definitely is going to be some kind of decimal. But the truth here is that there is a value, and we will show you how that value exists when we get to the graph. All right, so what is really going on here? Well, we got this x-intercept way out here at 104, and yes, that is correct. We also have some shifting. We have a graph that shifted to the left 4 units, but it also shifted down. Now, we're talking about that shift point. We're talking about that starting point of 1. So if I go to the left 4 units, I'm actually going to, and then go down 2 units, I'm actually going to be at the point -3, -2. Now, there's one more thing. There's an asymptote, and that asymptote shifted left, but it started at 0, so that means that it is going to actually be at -4. So how can we reconcile all this? Well, we've got a shift point, we've got a x-intercept, and we've got a log graph that always looks the same. It's always going to have the same basic shape. And now we see that there really is a y-intercept that exists. Apparently, the log of 4 minus 2 is going to be some little negative number. Now, if you did get out your calculator because you were just curious about the log of 4 minus 2, you see that it's equal to about about -1.4. So it does make sense with the position of all the rest of these points. But the whole point here is for you to be able to see that the shift to the left and down actually did create a shift point that was in line with the rest of this graph. What if we have a natural log? What if we want to graph a natural log? Well, I hope what you find out is that it's not a whole lot different than any other log. That is trying to find the x-intercept. Now that you've seen this a couple times, just plug that 0 in for y. Yes, you add 3 to both sides, and yes, you're going to base it with, well, with an e. Now, e to the 3, without your calculator, can just remain as e to the 3. With your calculator, you would be able to see that that does have value. And, you know, it's not a ginormous number. It's equal to just right around 20. But even if you didn't know that that was 20, we would still be able to say that there is no shift left or right, which means that my asymptote is going to stay put. There is a shift down, however. The shift down is going to affect the original starting point, which was at 1, and just plop it down 3 units. So now we're going to be at 1, -3. That's just a shift point. That's not like the intercept. But since we do have an intercept of e to the 3, we know that that's going to be some positive number. We actually know that it's right around 20. But the whole point here is that I can still draw the same type of log graph that passes through this intercept. It passes through the shift point, and of course it's going to approach this vertical asymptote. So a natural log graph, again, for all case and purposes, does not look much different than any kind of log graph. The only difference here is it has a base 3, so the exact shape of its curve would be connected to that base 3, but we're not going to see a difference when we draw one of these sketches for our purposes today. Now, I'd like to look at one more log graph with you that purposely has a negative sign on the log. Now, if you have a negative sign on any kind of equation, you want to be thinking reflection. What we want to do here, though, is be careful about what that reflection is going to do to the final position, the final direction, the final shape of this graph. But let's go through the steps before we just get a calculator out. You've seen me find the x-intercept almost always as my first step in all these problems. Let's not throw that away. Actually, if you plug a 0 in for y, you find out that the negative sign that we notice first off really just disappears, and so I can use a base e to both sides. Looks like I'm going to get an x-intercept, e to the 4th. Now, what should we do next? Let's talk about the asymptotes. Now, the asymptotes always come from a horizontal shift. There is no horizontal shift in this problem, so that means that the asymptote is going to stay put at x equals 0. So we've got an asymptote at x equals 0. We've got an intercept at e to the 4th. It doesn't look a whole lot different than any other graph that we've seen so far. So it looks like what we need to do is think about some shifting that does exist. Now, what you want to realize is that this 4 right here would be a 4 on the outside, and so that's going to be a vertical shift. So if you take your original starting point of 1 and you shift it vertically 4, you can get a point, a shift point that's part of this graph. That's going to be very helpful when it comes to drawing our final shape in a moment, which has to do with our reflection. Now, think about this with me. Whenever you have a negative put on an equation, it's always going to be a reflection over the x-axis. It's always going to be a reflection vertically. So if you think about the original shape of a logarithm, just a nice quick little original shape of a log, it will always possess this general direction. So if I flip this over the x-axis, that means that my graph is now going to be going this way. So we call this a reflected log graph, and it turns out that that purple graph fits perfectly into the points that we calculated, so that we can draw a graph that passes through our shift point and also the intercept. Now, students sometimes look at this and say, oh, that's exponential decay. Not exactly. That's just reflected. That's a reflected log graph. So it's not technically exponential decay, because exponential decay would have had to come from some equation that had a base and a negative exponent, like maybe e to the negative x. And although it looks similar, it turns out that they would not be exactly the same shape. So let's just stick with the language that this is a reflected log graph. Now, I've gotten a little bit sloppy with the domain. Let's put the domain down for this last problem. It's supposed to be pretty easy because even though this thing's been reflected, it still possesses numbers that are to the right of the vertical asymptote from 0 to infinity. Now, I get it. It can definitely be tempting just to type these in your calculator and kind of make it look like that you understand a log graph. I don't want you to just type them in the calculator, but I would like you to know what your calculator shows you. So if you graph 4 minus the ln of x, you certainly will see the graph, but you got to be careful. If I see something that's drawn on a test or quiz, that's going to give pretty good red flag that you don't understand what's really going on, that, well, there still is an asymptote, meaning that the graph really does not touch right here. It looks like it touches on the calculator, but it really doesn't. The graph actually goes up. It would go up very quickly. To possess that same behavior to infinity. So be careful. The calculator doesn't really show log graphs in theory as best as it should or could, but we could use it as maybe a checking tool to see that what it looks like to be reflected, and this log graph is still reflected as it's been flipped over the x-axis. All right, so when you do your homework, you want to be thinking about a lot of these no calculator strategies. There'll be some questions that allow you to further investigate and test your skills just as you've been accustomed to.